So the average speed is going to describe the average rate that an object is moving. So what that'll end up being, the total distance traveled over the total time taken. And if I go back to that bug example, the total distance that the bug traveled was 7 centimeters, because it traveled to the right 3, and then it traveled to the left 4. So that was 7 centimeters, divided by the total time that it took, and that was 2 seconds. So if I do the 7 divided by 2, I get 3.5. And then if I do centimeters by seconds, well, I still get centimeters divided by seconds. And so we would say 3.5 centimeters per second. So this, when you divide units and one's on top of the other, you can just say per instead of divide. But for a speed, you always need to have a unit of distance, inches, miles, kilometers, right, divided by a unit of time, which could be seconds or minutes or hours. But you always have to have a unit of length or distance divided by time. And so this would describe the average bug speed. It wouldn't tell you if the bug sped up or slowed down or stopped at all during that. This is just the overall average. I guess if we wanted to abbreviate this right now, maybe we could use an S for speed is equal to D for distance traveled. And you could do divided by T for time, or you could use a delta T now that we've learned that idea. The speed is equal to the distance divided by the time interval, or the change in time. All right, now let's do average velocity. So average velocity is going to be defined as the displacement, which was also the change in position, initial to final, divided by the time taken, or the time interval, however you would like to say it. But here's the thing. Remember that the displacement could be negative, meaning left for our bug. So it can be negative, indicating direction. Our average velocity would also be negative, indicating a direction. Can be negative, indicating direction. For an abbreviation, just because this would be a lot to write out all the time, we could say V for velocity, AVG for average, and for displacement, or the change in position, we could write delta X, and for the time interval, we could abbreviate it as a delta T. But if you actually want to calculate it, it might be easier to write it out as final position minus initial position, divided by the final time reading on your stopwatch minus the initial time reading on your stopwatch. For our bug, the final position was -1 centimeter minus the initial position of 0 centimeters divided by the final time, 2 seconds, minus the initial time of 0 seconds. So we end up with -1 centimeter minus 0 centimeters, so that's -1 centimeters, divided by 2 seconds minus 0 seconds, so 2 seconds. And I could rewrite that then as -1/2 centimeters per second. So the speed and the velocity have the same type of units, a length divided by a time. But notice that they're different values. That's because the speed cares about the total distance you took. If you made multiple loops or you backtracked on your own path, this cares about that. Whereas this velocity doesn't care about that. It only cares about the change between your initial and final position. It doesn't care how many loops or trips you may have made. It doesn't care. In the rest of the physics class, we actually use this one a lot more than we use this one, but you should have both. I'll take this time to suggest that you start an equation sheet and you keep some of the more important ones so that they will be easier to find when you need them for the homework or the test. Significant figures. These are going to be a non-ideal way for you to estimate other people's your precision in their measurements, and then if you're going to do math with it or record your own measurements, to write down your numbers so that way somebody else can interpret the precision of your values as well. So if you see a number like 300, is it very precise, like they measured it to be exactly 300? Or could it have been like 312, but they weren't sure, so they just wrote down 300? So what you would do is just assume that the 3 here is significant. They're like roughly 300. If somebody wanted to make sure to imply that their value of 300 was much more accurate, they could write it in scientific notation. They could have written it as 3.00 times 10 to the 2. Because we moved the decimal 1, 2 to the left. So that's why we have a positive 2 here in the exponent. And the reason why we would interpret this, the 3.00, to be a lot more precise is because somebody bothered to write the decimal and then these 2 extra zeros. So then we would interpret all of these digits here to be precise and meaningful. Whereas here we're not going to assume that these were meaningful. Maybe it was 312. But here it's definitely 300. This last digit here can be an estimate. Maybe it was 301, maybe it was 299, but they really are going to estimate that it was 300, and that 0 is important. That 0 was precise. For this class, really what I'll be looking for is that your final answer doesn't have any more significant figures than what information you started with. Round your final answer. So that it isn't any more precise. And by that I mean doesn't have any more sig figs. Than the numbers you started with. So maybe a homework problem would give us a distance, and let's say 301 centimeters. And how about a time interval of 2.7003 seconds. And with that information, they'd want us to calculate the average speed. So let's find the average speed. It's the distance over the time interval. And I would get 111.4690960 and blah blah blah. And then the units would still be centimeters per second. So now that I have my final answer, my average speed, I don't want to report this. I don't want to circle this because it looks very, 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 very precise. You can't know this any more precise than you know these. So here we would say that this number has 3 sig figs. The 3, the 0, and the 1 all imply that they're significant. They were measured In this case, the 2, the 7, the 0, the 0, and the 3 were all implied to be significant. So I would say this number has 3 sig figs, and this one has 5 sig figs. Right? So this is the least precise information that we started with. So our answer can only be precise to 3 sig figs. So we're going to keep the 1, the 1, and the 1, but this 1, the last digit that we're going to keep, might round up. So let's check after that. .469. Right? If it was 0.5, I would round the 1 here to a 2. But since it's 469, that's less than half, so we'll just keep that a 1. Right? So I could have rounded it to 112, but that wasn't appropriate here. Now that I've rounded it, I can circle it as my final answer. Right, so on page 16, the textbook does review scientific notation if you would like to go through and review it. And then I'll just move on to SI units. I'm like, granted, I'm American, so I'm like, how many miles is it to the grocery store? 5. But when I'm doing physics, I'm trained to think in SI units. And honestly, they're better. So the basic length unit in SI is meters. And the abbreviation for that is just a little m. For time, our unit is seconds, often just abbreviated as a little s. And for mass, which we won't deal with until we get to chapter 4, the default unit is kilograms, and its abbreviation is kg. So this set here is going to be our preferred set of units, but there are other ones like inches or centimeters, so we should also cover unit conversions. I don't mind if you use the internet or a calculator to double check your unit conversions, but be able to do it on your own by the time the test comes around. I'm going to show you how I do a unit conversion, but if you do it your own way, that's fine, keep it. So if you go into the front of the textbook or the back of the textbook, you should be able to find unit conversions. And it might say 1 inch is equal to 2.54 centimeters. But we could divide both sides by 1 inch, and that would just say that 1 would be equal to 2.54 centimeters divided by 1 inch. I'm like, they're different numbers and they're different units, but aren't they really the same thing? This is the length of 1 inch, and you're dividing it by the length of 1 inch. So really, it's just 1. But you could have done it the other way around as well. We could have divided both sides by the 2.54. In that case, we would have had 1 inch divided by 2.54 centimeters. It's just equal to the number 1 with no units. So this is usually what they'll give you in a table, but how we're going to use it is either this way or this way, and you have to choose which one is correct for your situation. So how about I convert 1 inch per year, which is roughly about how fast the mantle moves, and convert it into centimeters per second. So this is my starting information here on the left, and then I'm going to multiply by a conversion factor. I have inches in the numerator in the top, so I want them to be able to cancel out. So I write them down here. Top to bottom, they'll cancel out. Now inches, I would like to convert that to centimeters. Right, so now I know which one should be on the top and which one should be on the bottom. Centimeters is on the top, so I'm going to go over here and choose the right one. Centimeters is on the top. I choose this one. 2.54 over 1. Go ahead and cancel out your inches if you like. Now let's convert the years. Year. And I would like to convert it to second. And we could look it up in a table, but really in 1 year, there's going to be 3.15 times 10 to the 7th seconds. Right, and then the year, we have one in the numerator way over here and one in the denominator. They will cancel out. So then we basically have 1 times 2.54 times 1 divided by 1 divided by 1 divided by 3.15 times 10 to the 7th. And I prefer to use this square E symbol, kind of a capital square E on my calculator, which stands for times 10 to the. I just make fewer mistakes that way. So then I end up with 8.06 blah 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 times 10 to the negative 8th. 8.0635 times 10 to the negative 8th. And the units that had not canceled out yet was centimeters divided by seconds. All right, let's call this a perfect 1, as in it was 1.00000, because it's a conversion factor. And then let's say that this was significant to 3 sig figs. And for the 1 year, let's say that was a perfect 1.0000 year, so let's just ignore its sig figs. And then this 3.15, that's 3 sig figs. So far, I can't be any more accurate than 3 sig figs. But what did I also start off with? I said 1 inch a year. Now I guess, do you want to call that a perfect 1 inch per year? But I kind of was implying it's roughly the rate that the mantle moves, which is a rough estimate. So I'm actually going to just round this to 1 sig fig. So I'm just going to keep the 8 times 10 to the negative 8th centimeters per second. We don't count the 10 to the negative 8th in sig figs because all it really does is keep track of the decimal location. As far as prefixes go for the SI units, I'm going to ask you to know 3 of them. And kilo, which is abbreviated with a little k, basically means 10 to the 3, or 1,000. And then centi, like centimeters. And the abbreviation for centi is a little c. And an easy one for me is like there's 100 cents in a dollar. There's 100 centimeters in a meter. So it's 1/100th. So it's 10 to the negative 2, or 1/100th, 1 cent. 1 cent out of a dollar. And milli is just 10 times smaller than that. Millimeters. So the prefix would be a little m. And instead of 10 to the negative 2, it's 10 to the negative 3. Or if you wanted to write it out as decimal, 0.001. So now how about we take this value, this average speed, and convert it into our preferred SI units, and that would be meters per second. So I'll start off again with the 8 times 10 to the negative 8th centimeters per second. And I'm going to do a conversion factor. Centimeters needs to go down here, and meters needs to go up here. That way the centimeters can cancel out, and I'll be left with meters per second. Now here, it said centi was 10 to the negative 2. So that means 1 centimeter is equal to 10 to the negative 2 meters. Now, again, if you have a different way of visualizing this already, go ahead and use it. You don't need to take this approach or this technique. And then that would end up being 8 times 10 to the negative 10th meters per second. And then I would say that this answer is in preferred SI units, meters per second.